finally, what we have is what we call the hyperbolic functions. These are the last functions that we will see. So they are the cosine, the hyperbolic cosine, and this is defined like this: e to the x plus e to the minus x over 2, and the hyperbolic sine is e to the x minus e to the minus x over 2. Okay, and they look like this. So the cosine is kind of like a parabola, very wide parabola, and the sine is like this. Okay, so just like the cosine and the sine, the normal cosine and the normal sine, the hyperbolic cosine is an even function, and the hyperbolic sine is odd. Okay, now the hyperbolic tangent is again the division of the hyperbolic sine and the cosine. So then you have e to the x plus e to the minus x, and then e to the x minus e to the minus x, which is interesting because when x is 0, then this is 1 plus 1. Sorry, yeah, I made a mistake with the signs. The sine is on the numerator and the cosine is in the denominator, right? So when x is 0, this is e to the x minus e to the minus x 0. Okay, and so that's why the tangent is like this. It's also an odd function. Okay, so it's easy to see if you substitute minus x, it's tangent, the hyperbolic tangent of minus x is minus the hyperbolic tangent of x. It's easy to see. And so when x is very large, when x goes to infinity, e to the minus x gets very small, and this too. So the tangent, the hyperbolic tangent of x is very similar to e to the x divided by e to the x. So that's why it goes to 1 as this goes to infinity. And as it goes to minus infinity, these two guys become very small, and then you have minus e to the minus x divided by e to the minus x, so then you have minus 1. Okay, and similar to the hyperbolic cotangent, which is the hyperbolic cosine divided by the hyperbolic sine, and this is again e to the x plus e to the minus x, e to the x minus e to the minus x. And so the argument when x goes to infinity and minus infinity is very similar, so that's why the cotangent goes to this what we call this horizontal asymptotes. Okay, 1 and minus 1. But now here, when x goes to 0, this thing becomes 0. So then it's a diverging point, and then so the function becomes larger and larger and larger when you go to 0 from the right, and then it becomes smaller and smaller and smaller and smaller when you go to 0 from the left. Okay, so that's a very interesting aspect of the hyperbolic cotangent. And so finally, there are some identities that are very similar to the trigonometric identities for the hyperbolic trigonometric functions. Okay? It's easy to prove, you just need to expand this product of exponentials, that the hyperbolic cosine of x minus the hyperbolic sine of x is 1. And these two identities that look very, very similar to the ones of the normal cosine, normal sine, are also very, very easy to prove. Okay, so again, and this is why these functions are called the hyperbolic cosine and hyperbolic sine, because these identities and this they have a very similar behavior to the sines. Okay, so again, all of these properties, okay, you don't need to really learn them, but need to work with, you need to know these formulas and need to learn how to work with them. Okay, so what happens with you get this square, this what happens when you sum these two things like that. Okay, it's easy because it is just working with exponentials, but once you get familiar with these functions, you realize there are many things you can do with them, and they become useful for instance, integrals later on. And so I encourage you to work with them a bit, so that you can get familiar with them. And so that's it. That's the end of this video.